Okay, so here we go. In addition to explaining that last page of the PowerPoint, as promised, the other thing I want to do is help walk you through the lab so you can understand what you want to do or what you need to do to complete the lab. So let's start there. We'll work our way through the lab, and it's the last page of the lab that matches up with that last page of the PowerPoint. So we'll get to that. We'll deal with it when we get there. So page 1 of the lab is to apply the hand rule. Okay, what you see there are 7 separate conductors and 7 rows in the table, and they match up. Okay, so the first conductor on the left and the first row of the table are referring to the same thing. So what we see here is a circle. So that's our conductor. Okay, we've taken a piece of wire. Here's a piece of wire, and we have cut it, and we are looking at the end of it. So there it is. That's our piece of wire. Okay, so this is it. And the question is, what direction is the current flowing through that wire, and what direction are the lines of flux around that wire as a result of the current? Okay, so that's the task at hand. So if we look at the first row in the table, first thing it asks for, the first column is theory. So are we using the electron flow theory, or are we using the conventional flow theory? And we're told there on the table that we're going to use the electron flow theory. Second question, the second column, is what rule are we using? Well, these are all the conductor hand rules, so I filled that in for you. Okay. Third column is which hand are we using? So because we're using the electron flow theory, to figure this out, we are going to have to use our left hand. Okay, so this is going to be our left hand, which we're going to use to figure this out. There is one more detail here as well. We are told that the lines of flux are traveling clockwise around that conductor. So the question left is, what is the direction of current? So that's the final column there in the table, here looking at page 1 of the lab. So the question is, what direction is the current flowing through this conductor to result in lines of flux clockwise around that conductor? And so we're using our left hand because we're talking about current flow using the electron flow theory. And so our fingers are going to wrap around the conductor like this, and our thumb is pointing in the direction that the current is flowing through that conductor. So we're going to put a dot to indicate that that is the tip of the arrow pointing out of the whiteboard towards us, indicating the current's flowing out. Okay, so there, I've done the first one for you. So that's one of the 25 marks for Lab 2. You're welcome. Carry on and finish the other 6 conductors there on the first page and move on to page 2. So now page 2 is the coil hand rule. Okay, so what we're looking at here, to draw a coil, first we're going to draw a core. So that is the highly permeable core, the ferromagnetic material, some kind of soft iron, okay, which we're going to wrap the conductor around to create a coil. So here's the coil of wire wrapped around that core, just like that. Okay. Yeah, so the diagram shows us the first one on the left corresponds to the first row in the column. Shows us a DC power supply, the battery, and it shows us the polarity of that DC power supply. So remember that the long line is the positive terminal, the short line over here is the negative terminal. Okay, there's also an arrow on here, right there. Okay, so it tells us that this is the conventional flow theory. Okay, we have enough information there. We could have figured that out for ourselves. We can recognize that the arrow is telling us the current is flowing from positive through the coil to the negative terminal, and so that's obviously the conventional flow theory. Okay, what I want to indicate to you here, clarify for you, notice if you look at that first row in the table, go to the far right column, and it says current arrows, and it says up. But that arrow is pointing down, isn't it? Okay, but we could also put an arrow here that's pointing up. Okay, so up or down both seem to be a reasonable answer. So here's how we manage this. Okay, when I'm asking you about the direction of those arrows, I want to know the direction of the current through the conductor as it passes across the face of that core. Okay, that's where we're going to talk about the arrows. So this arrow was shown on the diagram. Okay, I put this arrow here for the purpose of our conversation, but really that's not where I want those arrows to be at all. Okay, where we want those arrows to be, so conventional flow theory, positive to negative, current's flowing this way and is coming up on that conductor right there across the face of the core. And it goes down around the back and up across the front, down in the back, up in the front, down in the back, up in the front. Okay, so there are the arrows showing the direction of the current through the coil right here across the face of the core. That's when we talk about the current arrows going up or down, that's the location that we're focusing on. Okay, because obviously it's going up and down and around, and because it's a coil rather, the current's flowing in every direction, so we have to pick a spot, and so that is the spot that we're going to choose to talk about. Okay, so let's see, what do we have to figure out? The source polarity. Okay, so if we move back one column, so that's the far right column about the current arrows. The source polarity is what I just drew right here. So we have the plus sign on the left, we have the minus sign, the negative terminal over there on the right. And that's what this is showing us, okay? Positive on the left, negative on the right. Okay, that's the polarity of the terminals of our DC power supply. Okay, that's what that second column from the right is about. Okay, so now we've got the two columns in the middle, the hand rule and the direction of phi. Okay, the direction of the lines of flux. Okay, well, the hand rule is pretty straightforward. Conventional flow theory means the right hand. Always. Conductor hand rule, coil hand rule, electron flow theory is the left hand, conventional flow theory is the right hand. Okay, nice and consistent. We don't have to try and figure out how that mixes and matches because it's always the same. So the question left is the direction of phi. The question is, here's our coil and our core, our electromagnet. Okay, is this the North Pole or the South Pole? Or is this the North Pole or the South Pole? Okay, that's what we have to decide. And so if you look at the second one, and I will always give you information in the table. If you just look a little bit further down in a different example, you can understand the kind of format and the sort of information that I'm looking for. So you notice in the second example there in the table, it shows north and south. Okay, and that's the same kind of information that we're trying to figure out here for the first one. North on the left or north on the right. Okay, so how do we do this? Well, now we're going to use our fingers to indicate the direction of the current, okay, as it wraps around. Which hand did I use? Which hand am I supposed to use? Conventional flow theory, right hand, means I better put my marker down for a second. So here we go. So my fingers are showing the current going up across the face of that core and down through the coil in the back of the core, behind the core, and my thumb is pointing to the north end of that electromagnet. So this is north and this is south. Okay? Now, moving away from the lab for a second, I want to carry on with this conversation just a little bit. Let me do this again, but just slightly different. So far it looks exactly the same, right? So there's my DC power supply with the positive terminal on the left and the negative terminal on the right. Okay, but watch what I'm going to do this time. Oh yeah, I just have to come down onto there. There we go. Okay, ugly, but effective. Okay, so watch what happens now. If we're still going to use the conventional flow theory in the right hand. So I'm just going to put that arrow right there for some clarity. Okay, here that coil of wire continued up on the face of the core. Here that piece of wire goes across the back first and then wraps and comes down across the front. Okay, and that's why it's so important for us to focus on the direction of current within the coil and across the face of the core, because until we get to that point, these two examples look exactly the same. But now, because we have wrapped the conductor into a coil first this way and the second time this way, we have wrapped the coil around the other way. Look at what happens. Okay, I still have to use my right hand. Here are the lines of flux. They're now going up in the back of the core, down across the face of the core, and my thumb is now pointing to the North Pole over here. So we have flipped the polarity of our electromagnet as a result of wrapping the coil around the core the other way. Okay, that's a concept we're going to return to when we talk about transformers as well, because we have a choice. When we build the coils of our transformer, we could wrap them one way or the other way, and we get a different type of transformer as a result. Okay, so that's just an interesting thing. Watch out for that. That's a detail as you're going through the hand rules. That's the sort of detail you've got to pay attention to and make sure that you get all the arrows in all the right places. Okay? Good. Moving on to Fleming's generator hand rule. Okay. So what we have now again, I'm going to do the first one. And we've shown 4 lines of flux as opposed to 100 million lines of flux. Okay, to get some perspective, the rest of this, we're zooming in a little bit to see what's happening. This is actually just one end of the bar magnet, and these lines of flux are all coming around like this. Sorry, that's supposed to be symmetrical. It's not even close. And now what we have is we have our conductor, and we're going to move it through those lines of flux. So here's the conductor, and here's the direction that we're moving that conductor, the direction of relative motion. Okay, so that's kind of the bigger picture of what we're looking at here. Okay, so let me see. The first one says we're going to use the electron flow theory, which means we're using which hand? The left hand. Okay, so here's my left hand. Okay, so let's see if I can do this. This is the North Pole. I've obscured it a little bit, but that used to tell us that that's the North Pole right there, which means these arrows on these lines of flux are going to be pointing up. That information goes the second column from the right. It says phi direction, so the direction of the lines of flux. Okay, they're pointing upwards, right, from north to south externally. So there are the arrows that we can put on our lines of flux. Okay, now hand rule time. Electron flow theory, left hand. Left hand. Forefinger flux. There are the lines of flux pointing upwards. Thumb is thrust, the direction of the conductor. The conductor's motion relative to those lines of flux. We're moving the conductor through the lines of flux in this direction. So when we create the third axis with our center finger indicating the direction of current, the current is flowing out of the board towards us like that. Okay, so there's Fleming's generator hand rule. We have a magnetic field. We have relative motion with the conductor cutting the lines of flux, and we get an induced voltage as a result, and current flow if there's a complete circuit on whatever that wire is attached to. Okay, so that is Fleming's generator hand rule. That's how you go through this page. So polarity, it's just asking for north and south. It's asking for the polarity at the end of the bar magnet that's actually shown in the image. Okay, it's understood that the other one is down here. Okay, but we're not showing that. That's just understood. Phi direction, up or down, right here where we're focusing on the lines of flux. And EG direction is the direction of the induced voltage, which again is this arrow, which is actually showing the current that the voltage would push. Okay, in this case, the dot means it's coming out towards us. Remember, the plus sign would indicate that that's the tail of the arrow pointing into the board away from us. Okay, there. So, Fleming's generator hand rule. Okay, now, as promised, let's figure out what's happening. I think I'll get this out of my way. I'm done with this. Let's figure out what's happening in an AC circuit. Okay, so I need to start by teaching you a little bit about alternating current. Okay. So this is a graph. Okay, this represents 0 volts. Okay, this is a positive voltage, and this is a negative voltage. Okay, and all that means is that the polarity has changed. Okay, that voltage, that pressure is now going to push current in the opposite direction. Okay, so it's going to push it one way, it's going to push it the other way. Okay, it's really all that's indicating. This, our x-axis, whoops, that's not an F, it's a T. Time. Okay, so over time, as we carry on, things change as time goes by. Okay, and it follows a very specific pattern. Well, actually, there are a number of different patterns. We're not going to get into those specifics. We're only going to worry about one pattern, and it's the sine wave. Okay, and so there's going to be an increase and a plateau and a decrease, and then it's going to change polarity, and it's going to do it all over again until plateaus and returns. Okay, my negative alternation, that's the term, positive alternation, negative alternation, as it alternates back and forth. When I draw it, my negative alternation always ends up bigger. That's not bad. It's pretty good. One idea, and we'll come back to this a little bit later, but rate of change is going to be a huge issue for us when we start doing all the math in the second half of the course. But the rate of change is steepest as it passes through 0. Okay, it's changing the fastest. Okay, the slope is the steepest. And it plateaus, and there is a moment when there is no change. It pauses there and there. Okay, we'll worry about more of that later. I just want to point out a couple of the features here as we go. Okay, but this is what you would get in an AC circuit, and the voltage is always changing, and therefore the current is always changing as well. The amount of current that the voltage can push is obviously going to change when you have more voltage or less voltage to push that current, or in the negative alternation, pushing it in the other direction. So there's an endless state of change taking place. Okay, so that idea brings us back to Lenz's law, and Lenz's law says that the induced voltage will always oppose the change that causes it. And so in a DC circuit where you have a particular voltage, say 10 volts, there is no change. So this is time, but over time nothing changes. Lenz's law becomes irrelevant. There's no application for it here because Lenz's law opposes change and there's no change. Okay, so it doesn't matter. Lenz's law is a really big deal in an AC circuit because change is happening all the time. Okay, so I need to make this smaller and slide it up into the corner. I wanted to start nice and big so we can look at it, but let's shrink it down. Okay, so here's the sine wave, and we need to look at, I wonder if I can squeeze 4 in here. I think I can. This is a conductor. So once again, cross-sectional area, there's our conductor. Okay, I've blown it up, made it nice and big. Okay. Let's break our sine wave into 4 quarters. Okay, so during this first quarter, okay, the voltage is positive and the amount of voltage is increasing. Okay, so we just have to flip a coin and start somewhere. Let's say, for the purpose of argument, let's say that a positive voltage is going to push current out towards us. Okay, so there's the current coming out of the board towards us. Okay, that current is going to create a magnetic field. So when we have to choose between the electron flow theory or the conventional flow theory, we will always settle on the electron flow theory. We choose to use that. We understand that it is technically correct. The conventional flow theory sticks around because it has some usefulness, mostly in electronics. But we understand that it's kind of the old archaic version, and we know that it's not quite correct, but it never really goes away. So my point is that when you have a choice, you're always going to choose to use your left hand for the electron flow theory. So there's the current coming out towards us. There are the lines of flux as a result. Okay? Now, I'm going to call this current, I'm going to give it a name because we have to talk about different currents now, because here's the voltage. So this is the applied, I should go to black. This is the applied voltage. That's the voltage applied to the circuit by the AC power supply. And so this is the applied current. It's the current that gets pushed through the circuit by the power supply. Okay, it's the one that creates this magnetic field. Okay, now let's talk about this change. The voltage is increasing, which means there's going to be an increase in current, which means there's going to be an expanding magnetic field. So the direction of motion is that way. The magnetic field is expanding, moving out away from the conductor. Okay, here's where things get tricky. When we start talking about the thumb pointing in the direction of the thrust, remember, it is not the direction of motion of the magnetic field. It is always the direction of motion of the conductor relative to the magnetic field. So let's zoom in on this space right here. And again, we can take any spot 360 degrees around. We can come up with the same answer. We can do it at the very top, the very bottom, the 9 o'clock position, the 3 o'clock position. It doesn't matter. I'm just going to do it right here. Okay? I'm going to have to stand on my head probably to do this. There are the lines of flux. My thumb indicates the direction of thrust. Well, which way is this conductor moving relative to that expanding magnetic field? The lines of flux are going that way, which means that the relative motion of the conductor is that way. Okay, so there are the lines of flux. There's the direction of the relative motion. There's the direction of the induced current. So I'm going to have to replace these arrows with some plus signs. And I'm going to call this induced current. Let's try it right here at the very bottom. Okay, lines of flux there. Lines of flux are expanding, which means the relative motion of the conductor at this point is away from those lines of flux. The lines of flux are moving away from the conductor, which means the conductor is moving away from the lines of flux. And now I'm going to have to move over here. There's the direction of the flux. There's the direction of the thrust. There's the direction of the induced current into the conductor this way. Okay? So when we draw the applied current and the induced current, the applied current goes right in the middle. The induced current we can draw around the outside. All right, and that's what you'll see when you look at the lab. Okay, any plus signs or dots around the outside indicate the induced current. One in the middle will be the applied current. Okay, so here's what we have. We said that Lenz's law is like inertia. And look at this. The applied current is coming out of the board towards us and getting bigger. The induced current is pushing back against it. There's the inertia at work. Okay? What happens next? Let's draw another conductor. Right here. Grab a different color. Had some red here a moment ago. Okay, let's look at this second quarter, it's still a positive voltage, which means the applied current is still going to be in the same direction. Here's the applied current, still in the same direction as it was in the first quarter. Positive voltage is going to push the current in the same direction, still more of it. Okay, which means left-hand conductor rule, there's the direction of current, there's the direction of the lines of flux. They're still in the same direction. But what's the magnetic field doing now? As we get a reduction in voltage, pushing less current, we get a reduction in that applied current, and now the magnetic field is collapsing. So let's take a look. We're going to work over here in this corner now. Okay, we'll get the same answer, right? We chose a couple of different places here, got the same answer. Let's try it right here. There are the lines of flux. What's the direction of the conductor relative to the moving magnetic field? The moving magnetic field is collapsing. It's moving towards the conductor, which means this edge of the conductor is moving out towards that collapsing magnetic field, relatively speaking. So there's the direction of the lines of flux. The conductor is moving in this direction towards the collapsing lines of flux, and the current is now coming out of the board towards us this way. Let's try it over here. Lines of flux, conductor moving out towards the collapsing magnetic field, and there's the induced current coming out towards us here. So once again, we have inertia at work. The current, the applied current, due to the applied voltage, is still coming in this direction, but we're getting less and less of it. So the induced current from that collapsing magnetic field is in the same direction, trying to keep that reduction in current from happening. Inertia, one more time. Okay, let's try the next one. Okay. So let's choose a different color and do this again. So we're into the third quarter of our sine wave. So what do we have happening now? Our applied voltage has changed direction, which means it's going to be pushing the applied current in the other direction. So in the first two instances, the current was coming out of the board. Now that current's going to be getting pushed into the board. We will draw a plus sign right there. That is our applied current. So what's the direction of the lines of flux around that conductor now? Left hand. Conductor rule, there's the lines of, there's the current, there's the lines of flux as a result of that current going this way. So the applied voltage has changed polarity, which means the applied current has changed direction, which means the lines of flux have also changed direction. Okay, now let's find out about our induced current. Okay. Well, what's happening here during this third quarter of our sine wave? The applied voltage is increasing, which means the amount of current is increasing, which means the lines of flux, the magnetic field, is expanding. Which means, let me see, where can I do this without having to stand on my head? Here are the lines of flux. What's the direction of the relative motion of the conductor? Lines of flux are expanding, which means this edge of the conductor is moving inward away from the expanding magnetic field. So we have flux, we have thrust, and we have the induced current as a result coming out here. Let's try it over here. Going this way. Now the relative motion is this way. So we've got flux, thrust, current. There it is. So one more time, the applied current is increasing, the induced current is pushing back against it, trying to keep it from getting bigger as the applied voltage rises. Do I have one more color? I think I've run out of colors. I guess I'll just use the black itself. So in the final quarter, oh, this black marker is not going to last. In the final quarter, yeah, try a different one. Better. Still a negative voltage, which means the applied current is still going to be going into the board away from us, which means our left-hand rule finds the lines of flux going this way around the conductor. Okay, we have a reduction in the applied voltage, which means we're going to have a reduction in the applied current, which means we're going to have a collapsing magnetic field, which means this edge of the conductor is going to be moving in this direction out towards that collapsing magnetic field. Lines of flux, oh dear, thrust and current, the induced current, once again going in this direction, probably easier over here. Collapsing lines of flux means the conductor is moving out towards the collapsing lines of flux. There's the direction of the flux lines. There's the direction of the relative motion of the conductor. There's the direction of the induced current as a result. And so finally, to complete the cycle, we have a reduction in applied voltage, which means a reduction in the applied current, which means a collapsing magnetic field, which means an induced current that's going in the same direction as the applied current, trying to prevent it from being reduced. It always fails, but it always tries. Okay? Good. So that's it. Okay, that'll allow you to get through the labs. This concept is a pretty big deal. Remember, one of the slides early on gave you a definition of inductance, and the definition was the ability for a coil to store energy in the form of a magnetic field. And this is it right here, okay? Because we are losing the magnetic field during the two cycles, the 2 points of the cycle where we are reducing the voltage. Okay, we are losing our magnetic field, but we are trying, okay, to hang on to it. All right, there's that inertia at work. We're trying to retain that magnetic field even at the point in time where it's dissipating. Okay, that should do it. That will allow you to finish the lab. If there are questions when you get into it, by all means, fire them off to me, either email or in Teams. And this is due midnight on Friday.